as time goes on. Yes? Why does it do that? Well, it's because charge is building up on this capacitor plate and it's changing the potential difference, right, across this resistor. And so the current decreases because the amount of current that flows through this resistor is proportional to the voltage drop across it, right? If the voltage drop gets smaller, the current goes down. The more charge it gets, the slower the current gets. That's why it's slowing down, okay? That's kind of the physicality of what's going on. The mathematics you've seen here.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Lecture 110, RC circuits. Before we start talking about RC circuits, however, we need to talk about exponential growth. And so to illustrate this, I want to consider a case. Let's say I start with 8 frogs. I'm going to draw 8 frogs. And then the next day I find that I have 12 frogs. I have 18 frogs. And then the next day I've got 27 frogs. Go ahead. What do you need? So if we write the frog population, we'll say n naught, the number of frogs on day 0, right, was equal to 8. How many frogs do we have on day 1? Well, we see we have 12. So why would we have 12? Well, if the frogs were breeding in pairs, and so that every day they bred a new frog, each pair of them did, right, we'd have something like this. 8 plus half of 8. That's the current population, right? And that would give us 8 plus 4, which is the 12 frogs that we have. And on the next day, we'd have the 12 frogs we started with plus half of 12 more. You see? That gives us the 18. On the third day, we have 18 frogs plus half of 18. It's 9 more. That's 27.
You're missing C in circuits.
You're right. I am. I could make this a capital C too, I suppose. There we go. That's a little better. So you see what's going on, right? Each day, the pairs of frogs that exist in the colony breed and generate a new frog for each pair. And so this is what the change in population would look like. Of course, we could write for day 4 and day 5, etc. But let's see if we can extrapolate a formula out of this. Instead of writing this equals 12, let's write this is equal to n naught, that's 8 from the day before, plus 1/2 n naught. But we can factor out n naught from this, and that would give us 1 plus 1/2 times n naught. You see that?
Yes.
What about on this day? And of course, n naught being 8, 1 plus 1/2, that's 3 halves, times 8, what do we get? 8 times 3 divided by 2, 12. So for the next day, what do we get? We're going to get n1 plus 1/2 n1, which is just equal to 1 plus 1/2 times n1. But we already have a solution for n1 in terms of n naught. So this is equal to 1 plus 1/2 times n1, but n1 is 1 plus 1/2 times n naught. So we get 1 plus 1/2 squared times n naught. You see that? And it would stand to reason then for the next day, it would be 1 plus 1/2 cubed times n naught. The fourth day would be to the 4th power, etc. So let's call this half, let's call it the rate. That's the rate of population change. And so I can write that n sub n on the nth day, sorry about the 2 n's, one is uppercase, one is lowercase though, is equal to 1 plus this rate. I'm just going to look at the in terms of like this formula, times n to the n minus 1. So whatever the previous day's population was, multiply that times 1 plus this rate, and that gives you the current population, the new population on the next day. You see?
Yeah.
But this rate, let's think of it as a change in the population per unit time. So that to get the actual rate, maybe I should call this r prime, I can rewrite this as 1 plus r times some delta t times n sub n minus 1. See how I did that? So now the rate of population change is the rate of population change per unit time times the amount of time. You see? So I can manipulate this. I'm going to distribute the n times n minus 1. That's going to give me n times n minus n to the n minus 1 plus r delta t times n sub n minus 1. I'm going to subtract n sub n minus 1 from both sides. That's going to give me n sub n minus n sub n minus 1 equals r delta t n sub n minus 1. Yes? Now I'm going to divide both sides by delta t. So we just divide both sides by delta t, and we just get a delta t over here. But I'm also going to recognize what n sub n minus 1. That's the change in population from one day to the next. So we can call this delta n if we'd like. So let me just call this delta n. Yes? And so we get that delta n over delta t is equal to r times n sub n minus 1, right? The population of the day before. In fact, I'll just get rid of the subscripts there. So you take the current population times the rate, and that gives you the rate of change of the frog population. But now let's think about calculus. Let's imagine that these delta n's become infinitesimally small, such that I can write this delta n over delta t instead as a dn dt equals r times n. So now I have what is called a differential equation. And the solution to it, you say, okay, if I could find a function n as a function of time, who when I take the derivative of it, it gives me r times the same function, then I would be good to go. Now you can solve this directly by cheating a little bit. Mathematicians, they hate this, but I'm going to treat the dn and the dt like parts of a fraction. And so I'm going to multiply the right-hand side by dt, and I'll end up with dn equals r times n dt, and I'm going to divide out n on both sides, so that just moves the n over here, and we get dn over n. And if I then integrate this, the integral on the right is easy because r is not dependent on t. It's a constant rate. And so I just get the integral of dt, and if I imagine that I'm going to go from time t equals 0 to time t, then that's just going to be rt. So this right-hand side will just be r times t. The left-hand side, we're going to integrate from n naught to some n of t, like this, and we have to recognize what the integral of 1 over n dn is, and that turns out to be a natural logarithm. And so what we get is the natural log. I always write natural logarithm like this. In cursive, it's just a habit. N of t minus the natural logarithm of n sub 0. And that's equal to RT. And then the properties of natural logarithms, you'll recall that when you subtract two natural logarithms, it's the same thing as the natural logarithm of n sub t divided by n naught equals RT. Okay. And the last thing we'll do is because it's a natural logarithm, what can we do to get rid of that natural logarithm? We can exponentiate it, right? So e to the ln, because e and ln are inverse functions of each other. So if I raise this to the e power, it undoes the natural logarithm. And so on the left-hand side, I'll just get n as a function of t over n naught equals, and on the right-hand side, I have to exponentiate also e to the rt. And the last thing I can do is I can multiply both sides by n naught so that I solve for n of t. Let me write that a little bit nicer. N as a function of time. So this is an exponential growth equation, you see? And if we were to graph it, it's going to look something like whatever t equals 0 is, that will be where it is here. I think it was 8 in this case. And it's just going to exponentially grow. If you were to differentiate this, we can verify that it satisfies this differential equation here. So if this is n as a function of time, then dn of t dt is going to be equal to the differential of a natural logarithm is just the natural logarithm again, right? But with the chain rule, we have to differentiate what's in the exponent as well. And the differential of that, rt, is just r. So I get r times e to the rt, which is just equal to r times n of t. And so you see that that works out just fine as far as satisfying this differential equation goes. So that's exponential growth. And in the homework, I give you a variety of problems. Oh, I should mention, if I want to make this into exponential decay, right, instead of growing, it decays, then all I need to do is just change the sign on the rate. So this is exponential growth, whereas this would be exponential decay minus RT. And so the growth is going to look like this, whereas the decay is going to look like this. So growth problem, in the homework I give you an example regarding type 1a supernova and the increase in brightness, the rapid increase in brightness that you see in a type 1a supernova. It's a little bit from astrophysics. And for the exponential decay, I give you a classic carbon-14 carbon dating problem. The mathematics of it's really easy. You'll probably find the problem challenging, just reading through it, trying to understand what is being asked of you. But the mathematics of it are really straightforward and simple. One more thing I'll note on exponential growth and decay is the idea of half-life and doubling time. So let's look at doubling time, because it's the same expression for both the half-life and the doubling time. It's just where you start is a little bit different. Are you still copying something down here? Okay, I'll give you a second. So if we wanted to ask how long does it take for, say, the population to double in size, how would we calculate that? Well, our equation, n of t equals n naught times e to the rt. This would be for growth. If it was decay, we would put a negative sign here. And instead of asking how long does it take for the population to double, because it never will, it's only getting smaller, we would say how long does it take for the population to become half, right, of what it currently is. So what does it mean to double? It means when is it the case that n naught times e to the rt, so at what time t, and I'll call this t sub 2x for double, when is that equal to 2 times n naught?
Yeah.
That's how I asked the equation to spit out for me the time it takes to double. You can see the n naught on both the left and right hand side. We can just cancel that out. And so it's really a question of when does e to the rt2x equal 2? Well, we've got an exponent. We want to get rid of an exponent. So what do? We take a natural logarithm. That's how we undo exponentiation, right? If I take a natural logarithm on the left side, I'm just left with r times t2x equals, and I do take a natural logarithm on the right hand side, I get ln 2, which is approximately 0.693. In finance, you'll hear something called the rule of 70. That's where they take the 0.693 and they approximate it as 0.7. Because now if I solve for t2x, the doubling time, I get that it's equal to ln 2 over the rate, r. And so if this was money, for example, this rate is a number always less than 1. 1 or less, right? But if I want to think of it as a percentage, then I take that and multiply it times 100. So since the numerator is 0.693, or approximately 0.7, if I multiply that times 100, it becomes 70, hence the rule of 70. But nonetheless, you take the logarithm of 2, which is approximately 0.693, and you divide that by the rate. So before our rate was a half, or 0.5. So if we took 0.693 and divide that by 0.5, anybody have a calculator handy? You could punch that in. 0.693 divided by, well, really it's just the double of this, right? So that's easy to do. You don't even need a calculator for that, right? So if r is 1/2, then this is just equal to 1.386, I think. Did I get that right? I think so.
Yes.
Okay. So 1.386 days, and you've doubled the population. Remember, on day 2, we already went to 12, so we're almost there. So just a little more, another third of a day, and we've got a population of, it's double what we started with, a population of 16. We started with 8, right? Yeah. So that's the doubling time. Again, the expression for the half-life is basically the same, except this would be ln of 1/2, which is just the natural logarithm of 1, which is 0, minus the natural logarithm of 2. On the left-hand side, we'd have minus r times t sub half, and we'd solve for that, and we'd get the time for the half-life. Okay, but it would be the same expression. If the rate was 1/2, it would be the half-life is 1.386 days. So that's exponential growth, and we'll need that for what we're going to talk about today, because we're going to talk about RC circuits. And the first circuit we're going to start with is a simple one. I'm going to take a capacitor of capacitance C, and I'm actually going to start with it already charged up, and a resistor of resistance R. And let me put a switch in here. That's how we draw a switch. Okay, and so when the switch is open, the circuit is off. Make sense? So at this point, if this capacitor is charged, right, what is it charged to? Well, if its capacitance is C, let's say we charge it, we need to specify something, either the total charge or the voltage. Let's say we specify the total charge. Then the voltage across these plates, right, all this the negative and this the positive, would be equal to the charge on it divided by C. And we'll call this Q naught, in fact. That's the initial charge. So if I put Q naught coulombs of charge on this capacitor, and it has a capacitance of C farads, then its voltage is going to be given by this equation here. And this is just based on the definition of capacitance. The capacitance tells us how much charge a capacitor will hold given a potential.
Yeah.
But as soon as I close this switch, what's going to happen? Remember, we've got, if there's charge stored on here, right, that means, in real terms, that means there are electrons built up on this plate, okay, that want to be over here, right? Because there's such a strong negative charge over here, Over on this side, we're going to have, these are metal plates. All the electrons will move away from here. We'll have positive charges on this side. But they have no way to get here unless the voltage is so high that it like breaks down in air or something like that, which happens to capacitors if you put too much charge on them. But the natural way for them to discharge is for me to close this switch. As soon as I close this switch, electricity will start flowing. Electrons will move around the circuit through the resistor, across the closed switch to this plate. But the way we, of course, talk about it is in terms of positive charge carriers. And so we talk about a positive, a current I flowing from the positive around here like this, yes?
Yeah.
So what initially will be the current? When I close this switch, so let me go ahead and close the switch now. There we go. Remind us that there's a switch there. I'll put that little node. The current, by definition, in this case, right, is going to be the rate of change of the charge, right? Since it's decreasing, the charge is decreasing, I put it in a negative sign. So when the switch is closed, under Kirchhoff's voltage law, or voltage rule, people get bent out of shape when you call it a law. It's not really a law. So I try to stick to Kirchhoff's voltage rule. The voltage here is going to be equal to the voltage here. So what are we going to have? Well, the voltage here, right, is given by V equals IR. The voltage here I've already specified in terms of the charge that I put onto it. So we're going to get that V naught is going to be, I'll call it V sub R for big R, for the resistor. Right, so that's going to be Q naught over C is going to be equal to I times R. But I, as I've already said, is just minus dq dt. So this is minus dq dt times R. But I want to let this, but the charge is going to change, right, as it discharges, right? So I'm going to, instead of calling this Q naught, I'm just going to call it Q. Whatever the charge is as a function of time, it's going to be equal to this. But let's look at that for a minute. If I solve this for dq dt, what do I get? I'll put therefore dq dt is equal to minus 1 over RC times Q of t. All I did was just solve for dq dt. Now, does this look like what we just talked about? Let me just write what we had for our population change. We had dn dt equals minus r n of t. Remember that? That's for decay. So this was for the decay problem. That's where the negative sign comes from. So you see that this rate r has something to do with this 1 over RC value. In fact, we call this 1 over this RC value the time constant. We'll call it tau for time constant, and that's equal to RC. That's the resistance times the capacitance. And we'll see what physical significance this has in just a minute. But let's just first recognize that this equation is essentially the same as this equation mathematically. And so that means that Q, as a function of t, the charge on this capacitor as a function of time, is going to be equal to Q naught times E to the minus R, not R, to the minus T over RC. I could have written over tau for the time constant. I think I will write it that way. That's how most people write it. T over tau, the time constant. What we really do when we look at circuits, right, is we measure the current through them, or the potential across something. And so what would be an equation for the current for this circuit that I have here? How do I get that? Well, right here, right? That's current, minus dq dt. The current I, as a function of time, is equal to minus dq dt, which means I just have to differentiate this term right here. I'll get minus, and then dq dt, what's the derivative of that? Well, it's going to be Q naught times the derivative of this exponent, exponential, which is just going to be e to the minus t over tau, because the derivative of an exponential is just the exponential. But by the chain rule, I have to differentiate what's up in the exponent. So that's going to give me a minus 1 over tau. So times minus 1 over tau. If we simplify all of that, the negative and the negative cancel. I get Q naught over tau times e to the minus t over tau. But Q naught over tau, this is a charge, this is a time. Charge per time is what? Well, another way to ask it is this. What is the current at time t equals 0? Now that we've solved this, right, we can plug in t equals 0 into this equation. If t is equal to 0, what is e to the minus 0? What is anything raised to the 0 power? 1. So that means that I of 0 is equal to Q naught over tau, which means that Q naught over tau is just I naught, the initial current, I naught. Where again, tau is RC. I want to draw a graph. Well, I'll draw it over here. So let's graph what this does. This is time, this is current. At t equals 0, we'll cross the y-axis here at Q naught over tau, right? So put Q naught over tau. That's the initial current. I can also draw charge, by the way. Let me just draw charge here too. T, Q, And at t equals 0, the initial charge is Q naught. So this is Q naught. And so what happens? Q naught will then exponentially decay. The current also will exponentially decay. So what is the significance of this time constant here? Well, if we were to assume that the capacitor continued to discharge at the initial rate, and that rate was constant and didn't change, the time constant is the time it would take, if I just simply draw a line with that slope of the time constant, this is the time that it would take, this time here, RC we'll call it, that's the time it would take for it to completely discharge. Now you can check that on your own. It's fairly simple algebra, but that is the kind of the significance of this time constant. Another way to say it is it's the time in which either the current or the charge, right, drops to 1 over e of its initial value. Because when t is equal to the time constant, we have e to the minus 1. So that's the time it takes for the current or the charge to decrease to 1 over e of its initial value. But I think the more meaningful thing to look at is to think of it in terms of its initial rate. If I allowed it to discharge with this initial rate of Q naught over tau, after a length of time equal to that time constant, right, it would completely discharge the capacitor. There would be no charge left. But that's not what it really does, because remember, the rate that it discharges at changes, it slows as time goes on. Right? That's part of this exponential process. So it, kind of mathematically, it never gets to 0 charge. It just approaches it at t equals infinity. Make sense? Okay, so this is a simple RC circuit for just the discharge portion. What about charging one of these guys? How would we charge a capacitor? Well, let's look at that next. It's a little more complicated, but it's not terrible. Obviously, we need a battery or something to charge it, so we'll use a battery. So we would take a battery with some EMF. Again, I'll put a switch in here for now. Are you blowing on a harmonica?
I was.
Why?
Not sure.
Okay. Yeah, so we'll do this. Put the capacitor here, and then I'll just put the resistor here. I'm terrible at drawing resistors. So there's our resistor, there's our capacitor. Here's our switch. Here's our battery. You'll recall the plus is here, the minus is here. This is the circuit we would use to charge this. We would close the switch, and as soon as we do, this capacitor will begin charging. Why? Because there's a potential difference across it. This side of the capacitor is connected to the negative side of the battery, and this side of the capacitor is connected to this resistor, which is connected to the positive side of this battery. So current will start flowing through this way, and it will start building up charge on this plate of the capacitor. So how can we analyze this? We can use Kirchhoff's voltage rule. So what would that say? It says that here's a loop. The voltage change across the loop is 0. So here we have a positive change in voltage, the EMF, E. Here we have a negative change, that's minus IR, whatever I is, right? And here we have another negative change, that's minus Q over C. That's the voltage, the potential, that's the voltage across the capacitor. So this means that, of course, that I is equal to IR plus Q over C. But let's replace I with dQ dt. So I get dQ dt times R plus Q over C. And we have ourselves another differential equation, but before we solve it, or at least allude to its solution, let's recognize like some limits on this. Let's say that the capacitor is fully charged. If the capacitor is fully charged, then there's not really going to be any current anymore, because its current stops flowing once the capacitor is fully charged. So this term here, this current dQ dt is going to go to 0, which means that E is equal to Q over C. That means that the charge Q will just be C times the voltage, which makes sense, right? So that's the amount of charge that would be on the capacitor if it were completely charged. The EMF times the capacitance. Initially, if we ask, well, what about initially? In the very, very beginning, right, there's no charge on the capacitor, so this term is 0. And what do we get? It says that the current I times R is equal to the voltage, the EMF. So that says that I is equal to the voltage divided by R, right? This is just Ohm's law.
Yeah.
So we have Ohm's law initially, and then we have a fully charged capacitor, right, in kind of the asymptotic limit in time as t approaches infinity. But we can, of course, we can solve this, and we've seen it before. Let me just, what lecture was it? Lecture 107, we had this equation. This is when we were talking about drift velocity for electrons. We had this equation, and we found the solution to be, did I say voltage? This is velocity, sorry. This V here is velocity. We found that the solution to this differential equation was tau QE over m times 1 minus e to the minus t over tau. This is the solution that we found for the differential equation. And you can see that this and this are fairly similar, mathematically anyways. They have nothing to do with each other otherwise, but mathematically it's the same math. It's the same differential equation. So we can solve this to find that Q, as a function of t, is equal to C times the EMF times 1 minus e to the minus t over tau. It just follows by analogy from this. If you want to see how, I think we derived it. I think we solved the differential equation in the lecture 107. But I forgot to look back at it and see if we actually did that or how we did it. And nonetheless, in the homework, I give you a problem where I ask you to verify that this solves this differential equation. It just means you have to take a derivative and plug things into that formula and see that it left equals the right. Okay, it's fairly straightforward. You can see it's almost like what we had before, except we have this additional term here, right? So it's CE, what is that? That's the initial charge. Or not the initial charge, but that would be the fully charged capacitor. Minus the fully charged capacitor times some exponential decay. You see?
Yeah.
Make sure I got the sign right on it. Yes, good. Now, what about the current? Well, the current is just the derivative of this. So I, as a function of t, is just dq dt, which is just going to be epsilon over r times e to the minus t over tau, where tau, again, is equal to RC. Some people call it the RC time constant. Right? If you take the resistance and the capacitance, you multiply them together, you get a time. And if we look at a graph of what the charge looks like, the charge buildup over time, of course, we start out with 0 charge, right? And we're going to build up until we reach, we're going to approach asymptotically this kind of fully charged state of CE. EMF times the capacitance, right? That's the charge that would be stored on the capacitor if it was fully charged. And you'll see that slowly it builds up over time. This time constant in this case, if you were to take the initial rate of current, right, at t equals 0, this E over R, then this time, RC, is the time it would take to charge it to full charge, you see? If the rate didn't change. So it starts out at this rate, then the rate obviously decreases, because you can look at it, it's just the tangent line at any point along this curve, right, would be the rate of charging, because this is charge versus time, yes?
Yeah.
There's not supposed to be a hole in this function, by the way. I just put my finger there, I think. Yeah, so again, interpreting the time constant, right, as this time period over which, if the initial rates were sustained throughout, for things to complete, either to fully charge or fully discharge, is the best. That's the best way to think about it physically. Mathematically, it means it decays to 1 over e of its initial value, and that's not so useful. But anyways, so there's that. Relatively straightforward, just an application of Kirchhoff's rules. The voltage around any loop is 0. Gives you a differential equation. You solve that differential equation, and you see that charge either exponentially decays from or exponentially increases to some value. Let's do a simple problem. Let's put some values on this. Let's let this be, I don't know, 1 kilo ohm. And let's let the capacitor be, what did I do in my example? 2 microfarads. 2 microfarads. And let's ask, hey, what is the initial current? Right? So what is I naught? Well, I naught is just the EMF over the resistance. Maybe I should write the original equation. Well, that's fine. Oh, I should specify what the EMF is here, right? So the EMF, we'll say, is 12 volts. 12 volts. 12 volts. So here we've got 12 volts over 1,000 ohms. Oh, I see. I use 10 volts in my example just to make the math easy. Right? So 10 over 1,000, right? That's the same thing as 1 over 100 amps, which is 0.01 amps, right? So that's the initial current, 0.01 amps. B, and there's a homework problem where you're asked to do exactly these things. What would the final charge be? I'll call it Q sub F, Q final. Once the capacitor is completely charged up, what's it equal to? Well, we know what that is. That was the other asymptote in our differential equation, the EMF times the capacitance. Well, the EMF is 10 volts, and we're going to multiply that times 2 microfarads, which is 2 times 10 to the minus 6 farads. And so that's going to be 20 microcoulombs. Just keep it in micro. So 2 microfarads times 10 volts is 20 microcoulombs. Not very much charge. C. What is the time constant? In other words, if you were to charge this at the same rate that you initially start at, how long would it take to fully charge? Well, that's just RC. Let me write. Time constant equals RC, which is R was 1,000 ohms times C is 2 microfarads, which in this case I think I want to do it in farads. So we'll do 2 times 10 to the minus 6 farads. And this we'll write as 1 times 10 to the 3 ohms, minus 6 plus 3, right? We're going to get 2 times 10 to the minus 3 seconds, which is just 2 milliseconds. So 2 milliseconds. And then D, so how long does it take to reach 99% charged? Well, this is a problem that's like what we did in the very beginning when we talked about doubling time. So we want to know 0.99 times Q naught equals Q naught times E to the minus T over the time constant, RC. Maybe I'll put the RC in here for now since we know we're going to want to plug those values in. The Q naughts, oh, sorry, it's the wrong formula, isn't it? It's not equal to, it's Q naught equals Q naught times 1 minus E to the minus T over RC. Sorry, I should have left it up there, huh? Q naughts cancel. I'll move this to the right. So I have E to the minus T over RC equals 1 minus 0.99 is just 0.01. Take the natural logarithm. Remember, this is really 1 over 100. If I take the natural logarithm of both sides, I'll get minus T over RC equals the natural logarithm of 1 over 100. But that's equal to the natural logarithm of 1 minus the natural logarithm of 100. The natural logarithm of 1 is just 0. Got a minus sign here, a minus, and on the left-hand side, we're going to get, oh, here it is. Get rid of this minus sign and this minus sign, and we have that T equals RC times the natural logarithm of 100. And if you plug those numbers in, you're going to get 9.2 milliseconds. 9.2 milliseconds. So compare that with the time constant, 2 milliseconds, right? It's much slower to charge it because the rate that it charges decreases as time goes on. Yes? Why does it do that? Well, it's because charge is building up on this capacitor plate and it's changing the potential difference, right, across this resistor. And so the current decreases because the amount of current that flows through this resistor is proportional to the voltage drop across it, right? If the voltage drop gets smaller, the current goes down. The more charge it gets, the slower the current gets. That's why it's slowing down, okay? That's kind of the physicality of what's going on. The mathematics you've seen here. All right, well, next time, that's it for... we're going to move on next and talk about magnetism, right? Because this is about electricity and magnetism, and so magnetism we haven't even talked about yet. That's what we're getting to next. So the next lecture will be on magnetism. All right, see you then.